Hello everyone, welcome to this week's SF Seminar, episode 35. Today we are excited to have Mihir Prabhudesai, a first-year PhD student at CMU Robotics, join us. Mihir's research focuses on representation learning and generalization in deep learning. The talk today is titled Diffusion-based Autoregressive in Data Constraint Setting. Please join me in welcoming Mihir for his talk. I'll hand it over to you.
Okay, thanks for inviting me. Okay. I mean, yeah, feel free to like ask questions in between and stuff like that. Uh, okay, so progress in AI in the last 5 years or so has been mainly due to scaling two things. One is compute and one is data. Like in the last 5 years in LLM, we have pretty much kept scaling this and we keep getting better and better results. But the issue is that compute is growing, but data is not growing. And I think Ilya did like a very good job at explaining this. So he was invited for a test of time talk at NeurIPS, and the main slide from his entire talk was this, which is pre-training, as we know, will end. Compute is growing. Oh, I think maybe we can do like admit all or something because it keeps coming in between. Uh, like the mm, Okay. Yeah, so pre-training, as we know, it will end. Computers growing, better hardware, better algorithms, larger cluster, but data is not growing. We just have one internet, which is equivalent to the fossil fuel of AI. There are papers that study this more properly, and there are predictions that the rate at which uh, LLMs are consuming data, but the rate at which unique data is growing on the internet is somehow starting to match. Like we are saturating in terms of the amount of data that is available, and they expect that by 2028 we would lose out of unique data to learn from the internet. Um, so given that we could become data constrained and the scaling trend might not hold, it's critical to look for algorithms that are more data efficient to keep the scaling trend going. So primarily, there have been two algorithms that have worked out really well so far. One is autoregressive objective, which was proposed in GPT-2 in 2019 from OpenAI. And the second is diffusion objective, which was presented in Vision in DDPM from Berkeley people, Jonathan Ho, Ajay, and Peter. And both objectives are very similar in the sense that both maximize the joint log likelihood. The main difference that comes between the two objectives is the way they factorize the joint. So both have their own way of factorizing the joint. So like success of diffusion and autoregressive that happened in 2019 and 2020 created both excitement and confusion. So language community, for instance, because diffusion was first presented in Vision, language community started exploring diffusion on text. So it started with a D3PM paper, which is a very good paper, who introduced the idea of discrete diffusion on text. And similarly, Played, where they tried to do continuous diffusion on text, which is like add Gaussian noise. Similarly, and like a lot of papers have been on diffusion on text since then, since the D3PM paper. Uh, Similarly, in vision community, people started exploring autoregressive on images. Uh, for example, there is party paper that came out which scaled up autoregressive image generation to like 22 billion or something, and VAR also does some form of autoregressive. And there have been a lot of papers since then that have started exploring autoregressive on images. And in robotics, there is like even confusion, like people are trying both autoregressive and diffusion. So there are papers like diffusion policy and all of these that are trying diffusion in robotics, but then there are also papers that are doing autoregressive. So there's a lot of confusion as to like what is the right way to go about. So I'll just give a quick background on how autoregressive LLMs work. So essentially, you want to maximize this joint log likelihood of this tokens, the L tokens in the sequence, and you factorize the joint in a left to right way. So basically, you try to predict the next token given all the previous tokens. Um, the way diffusion LLMs work is a bit different. So if you remember in continuous diffusion, there was this idea of adding noise. So what you do is like you have this X, which is the input, and then you add noise in your forward diffusion process. And in continuous diffusion, the noise is sampled from Gaussian noise. In discrete diffusion, instead of sampling from Gaussian distribution, you sample from Bernoulli distribution, and you essentially are like doing random masking at that point. So you're randomly masking out tokens. So it's this. So there's still an idea of forward diffusion. It's just the noising strategy is a bit different, or the noising distribution is a bit different. And then like since you have forward diffusion, then you also have you also have reverse denoising process. And in discrete diffusion, the objective ends up being something like this. So you're still maximizing the log likelihood. It's just like you're given the mask tokens, you're predicting them back. You're masking random tokens and you're predicting them back. Now the issue is like prior works in diffusion uh, like don't show that great results. So just to put things in perspective here, for example, this is perplexity, so lower the better, and this is like perplexity from two popular diffusion models. So the above one is continuous diffusion, and the middle one is discrete diffusion, which is MDLM, and they're still like quite worse than autoregressive, and autoregressive is still quite better. And there are papers that have built scaling laws on diffusion language models. And what they have found is that diffusion requires up to 16 times more compute to achieve the same negative log likelihood, or like to achieve the same validation loss in a way, which in diffusion is the negative elbow. So to put things in perspective, this would be like, imagine if you're putting like $10 million on your pre-training, then now you have to spend something like $160 million to achieve the same validation loss, which is like not a great trade-off. Um, so like our idea was that the issue with prior works, which show that the 16x worse for diffusion, is that they conflate data and compute in a single plot. Like in the sense, because they operate on single epoch setting, it's not clear whether diffusion requires just 16x more compute or 16x more data, because you keep increasing data as you increase compute, following the chinchilla paradigm. And that's why in this work our main contribution is like we build scaling laws for diffusion by disentangling data and compute. So we study diffusion and autoregressive models in data constraint settings. So this is our work. Diffusion beats autoregressive in data constraint settings. So the motivation to pursue this project was very simple, which was that like if you look at the diffusion training objective, like essentially you're doing random masking and then you're training the model to recover all these possible maskings, and you keep training over different masking masking types. But if you look at it interestingly, like left to right masking gets included in the diffusion training pipeline. Like if you're doing this random masking with a specific schedule, like there is a non-zero probability that you would mask tokens in a left to right order, something like this. So the hypothesis was like you could interpret diffusion as like some form of implicit data augmentation on autoregressive. So there is left to right masking happening, but there are all these other possible maskings also happening along with it. And like I mean, from computer vision, if you like, one simple thing to know is that if you're doing you should only do data augmentation when you're data bottlenecked. Like if you're not data bottlenecked, then you should sample from like the distribution that you think is more closer to reality. Um, so and the reason why maybe prior works get worse results for diffusion than autoregressive is because everyone trains diffusion LLMs, or most people train diffusion LLMs in single epoch settings. So So we studied diffusion models in data constraint settings. And for this, we trained about 200 plus diffusion and autoregressive models at different uh, data set and flop budgets. So I think this slide pretty much characterizes like the whole paper in a way. So here, what we are doing is we are studying for 100 million unique tokens, and this is like the chinchilla optimal on the number of flops you're supposed to be training for one epoch. And here each dot represents like a model trained until conversions, like until the epochs that we had decided it for. And if you see the autoregressive loss curve, like it reduces, and then after a certain amount of flops it starts to saturate and there is no improvement in loss. But if you do the same for diffusion, you find this interesting trend where initially it's a lot worse than autoregressive until a certain point, and after a certain point it starts beating. And we call this as like critical compute point. And we find this to be true over different unique data budgets. So we tried this on 100 million, 50 million, 25 million, and even 500 million. And we found that you always have this critical compute point after which diffusion starts to beat autoregressive. Um, So then, I mean, there are two ways of increasing compute. One is like you increase the number of epochs in data constraint settings, or you increase the number of parameters in the model. So we try to disentangle these two ways of increasing compute in this plot. So here, this blue part is for autoregressive, and this red one is for diffusion. So I think first thing to note is that if you look at the one epoch loss, like autoregressive is clearly better, which is like 7.07 versus 10.65. Uh, and one more thing to note is that autoregressive achieves its best loss, which is like the least possible loss or the global minima at about 50 epochs. And if you train beyond this point or with more parameters, it's like shows all these overfitting trends. Diffusion, on the other hand, like shows its best loss at about 500 epoch, and even after 500, like we still couldn't make it overfit that easily. So we just stopped there because we just didn't have enough compute. Um, and the last important thing is like if you look at the best loss that diffusion achieves versus the best loss that autoregressive achieves, diffusion has a better loss, like 3.55 versus 3.71. So given like we train like so many models which are 200 plus models, we like our goal was to fit scaling laws on these models so that we can use them for some predictive analysis. So this is the standard scaling law equation, which was proposed in like the Chinchilla paper and the OpenAI paper. And this is specifically for single epoch settings. So N here is the parameters, D is the training tokens, and these are some learned constants, and then you use this to predict the loss. Now, some like I mean, Moningov et al. In their NeurIPS paper, which was like 2023 outstanding paper, in that they generalize this to data constraint settings, where they define these two terms n hat and d hat, and n hat is like the effective number of parameters and d hat is effective number of tokens. And essentially like d hat ends up becoming like this geometric progression where u is the amount of unique data that you have, and every time you see this is like every time you have an epoch, and it's like a there's like a decay factor to it. So every time you do an epoch, you lose some value out of it. And if you just analytically solve this equation, then you get something like this, where RD star is equivalent to like the half life of data reuse. So RD star is a learned factor, and if RD star is very high, that means you can train for a lot more epochs before having like a meaningful reduction in your loss. And this was proposed in the NeurIPS paper. So we use their formulation to fit. So they had fitted for autoregressive models. So we use their formulation to fit it for diffusion models in data constraint setting. And the main term to look at is this RD star, which is the half life of data reuse. And if you see, then for autoregressive, it's like about 30 epochs. So after training for, so half-life would be like after training for 30 epochs, you have like a meaningful reduction in your, like the improvement that you can have in your loss. So repeating after that point will give like significantly diminishing returns. And for autoregressive, this is about 30 epochs, but for diffusion, this is about like 500 epochs. And the decay rate is also quite visible from this plot. So here, what we are doing is like the dots that you see here are empirical points, and the curves that you see here are the fitted curves. So one thing to show in this plot is like the fitted curves follow the empirical points. And another thing to note here is that as we are reducing the data fraction, there is a decay. You can clearly see a decay in the blue curve, which is the autoregressive one, where it's slowly starting to decay as you're reducing the data fraction. But in diffusion, the decay is very low. Like the decay factor is not very clearly visible, and it's visible from all these three plots pretty much. And the way these plots are created is like you're studying over three different flop counts, and then you use these flop counts to do the 100% training. So you have like 100% of unique data, and then in 50% unique data, you are using 50% of the unique data and you're repeating two times. In 25%, you have 25% and repeating four times. So you're maintaining the number of flops, but you're still trying to study on how the decay factor is affecting as you're repeating. So this makes it a bit evident. Um, and this is also a similar plot, but in this, what we are showing you is the loss curves, the validation loss curves, where 2 epoch is like the same setting where you're training for 2 epochs with 50% of the data, and 100 epoch is like you're training for uh, with 1% of the data, you're training for 100 epochs. And if you see an autoregressive, you clearly see this divergence between all of these loss curves as you're changing the number of unique fraction. But in diffusion, all the loss curves look pretty similar. Yeah. And you could potentially like use these scaling laws to extrapolate to see like how the trends look like. And one thing that the Nurev's paper, Moningov et al.'s paper had found was that in autoregressive, repeating for 4 epochs is almost as good as having new data or having fresh data. So the loss that you achieve after having fresh data or all unique data would be equivalent to having training for 4 epochs. And for diffusion, we find this number to be 100 epochs. So repeating until 100 epochs can give you similar loss as having all fresh data. Um, yeah, pretty much. And we find that, I mean, the thing that we do in this paper is we take we more focus on the validation loss, and what we do is we take the models that achieve the best validation loss and use that for downstream evaluation. And we find that these like the validation loss translates to downstream. So diffusion on average seems to do better across downstream compared to autoregressive. And we also go in finding like when to use diffusion over autoregressive. So because you have fitted these scaling laws, you could try to understand is there like a equation that you could predict where you can, let's say, estimate the number of flops after which diffusion starts to beat autoregressive. And you could get this by just simply solving this equation. So you have like the loss of diffusion and you have the loss of autoregressive, and when the difference between the loss is equal to zero, at that point you have found your critical compute point. um, and we solve this like we solve this using just doing symbolic regression. So we just plotted these points that we found, and we somehow surprisingly found that it was like a power law, like a perfect power law. So we just use linear regression in log space to fit it, and the equation turns out to be something like this. So this equation can allow you to predict, let's say, at what flop count does diffusion start to outperform autoregressive. And it looks something like this. So if you're in the red, if you, on the left figure, for instance, if you're in the red region, if you plot the amount of unique tokens and flops you have, and if you're on the red region, then probably you should use diffusion. If you're in the blue region, you should use autoregressive. And we also find this to hold empirically. So here the stars are like the empirical points. and the dots are the theoretical ones, and we find that it somehow holds even empirically. um, so overall, like the conclusion was like, if you're compute bottlenecked, maybe autoregressive objective is a better one for you, but if you're data bottleneck, you should use diffusion. And I mean, my advisor does a lot of robotics, so like in robotics, it would mean that in simulation training, so in robotics, there's a thing called sim to real. So if you're doing sim to real, then autoregressive is a better objective. But if you're doing real world training, then diffusion becomes a better objective, because in real world, you're data bottlenecked. But in simulation, because data is free, you can just run the simulator, your compute bottleneck. And to be honest, like if you just see the trend that is happening in robotics, this somehow already happening. Like people who are doing real world training are resorting to diffusion objectives. Simulation hasn't scaled, but I would argue, there are more papers doing autoregressive in simulation than diffusion. So I mean, so in this current form, we archived our paper, and then we had like some Twitter peer review after this. So like Clone of Simo posted our paper, saying that everyone get your top 1% data and train 100 epoch, top 1% quality data and train 100 epochs right now. I mean, it's a very smart statement. uh, and then Lucas like said something, which is that AKA data augmentation. This number actually matches my experience exactly. This is something I think LLM people will not sure how they can write the whole paper and not even once think of running the AR with augmentation or dropout. Now the thing is, like, we had actually run AR with augmentation or dropout before even submitting the paper. We just didn't include it in the paper because we didn't get any positive results. So when we ran it, we didn't see any improvement in terms of uh, like the overfitting point or data efficiency. So we thought, okay, maybe we can't explain, so maybe better to leave it. So we didn't include it. So but actually we should have included it. So then we rebutted him, and we gave a rebuttal saying that, okay, we ran all this. We ran even more than what we had run before. The overall conclusion was that, like, when you try all this attention drop and token masking in autoregressive training, you don't really see much benefit. The default dropout and default settings are still the best, which is the dark blue curve here, and the red curve here is the diffusion best loss that you achieve from 500 epoch training or something. And so we wrote him our rebuttal, and the main thing that we said in the rebuttal was this paragraph, which is like, which was our hypothesis as to like why this doesn't make sense, which is that diffusion models, if you think of diffusion models, they're in their objective, they're somehow, I mean, they're not exactly randomly factorizing the joint, but implicitly they are in a way like somehow randomly creating different partitions and training using them and all these different conditional tasks. So, and we think that this enables them to generate tokens in random order, which you can't recreate it by simply random input masking while still having the next token prediction objective. Uh, so then he replied to our rebuttal, and I think the main thing he's saying is this, which is that, like, he suggested us a good idea. So what he told us was, okay, so if this is your hypothesis, then maybe you should try this experiment, which is actually a very very smart experiment. And what he suggested was like, so at the beginning of the training, you start with n permutations, uh, and like before starting the training, you start with n permutations, and n is equal to 1 would be regular autoregressive, and n is equal to 2 would be autoregressive with a random permutation. And the model can figure out what the permutation is because your number of permutations will be limited. And then what he was expecting is like, as you keep increasing n, if the hypothesis is true, then you would see the loss reducing, that it's learning from all these different token orderings. So we tried this experiment out, and overall, like, I'll just explain what the experiment we ran was. So mainly it's something like this, where if you see the standard AR, which is the blue curve, and the red one is still the diffusion one, and we're training for 100 epochs here. And if you do n is equal to true, then you get like the overfitting point moves a bit on the right, and you get lower loss as a result. And then with n is equal to 4, it moves even right, and then with n is equal to 16, it moves even right, and you keep getting better and better loss. If you look at the losses over here on the 100 epoch point, then you clearly see a trend where autoregressive is the worst, like the standard autoregressive was worst, n is equal to 2 is much better, n is equal to 4 is even better, n is equal to 16 is even a little bit better, and slowly you're approaching the diffusion loss at the end. So, and one more good thing about this experiment is like it could potentially allow you to interpolate now between like between data and compute efficiency. So overall, like data and compute are like two things that you have to trade off. Like, do you want to be compute efficient or data efficient? It's tough to get both. So ideally, what you want is like you want to stay on the Pareto front of data and compute efficiency based on the resources you have. And one thing before doing this experiment, we had mentioned in our limitation of our paper was like ideally you want to interpolate between these two objectives. So I believe like this, like something like this could potentially in the future allow one to interpolate, and someone could study these Pareto fronts and better understand these trade-offs. Um, so then after this Twitter drama or X review, there was another X review that happened. So 3 weeks after we released our paper, another concurrent work came out, and the overall like the good thing is like they validated our core finding, which is that diffusion beats autoregressive in data constraint setting. So they focused on a different thing than us. So we focused more on the validation loss, and we tried to find this crossover point in the validation loss, and then we use the best validation loss to evaluate on downstream. They instead had a different thought process that let's not focus on validation at all. Let's just directly go to downstream. So they even studied like performance of downstream performance on overfitted models, underfitted models, and everything. And overall, the conclusion is the same, that you get this crossover point after a certain number of epochs. Before the crossover points, autoregressive is better. After the crossover point, diffusion is better. And yeah, so I mean this is cool. So but I mean but like still like diffusion, I mean still we need to do a lot more to make diffusion like actually practically competitive with autoregressive in industry, for example. But these are some signs that could someone could work on to make this better. Yeah, I mean, yeah, this is all my talk.
Yeah, thanks for your amazing talk, and thanks for this Twitter rebuttal. Does anyone have any question? Feel free to unmute yourself or just drop the question in the chat.
Hello.
Hello.
Can you please explain a little bit more details about the experiment with permutation for the previous slide? So
Sure.
how do you permute?
I mean, so I think I mean I can maybe like just show the Twitter. I explained it on Twitter. I think I posted like a pseudocode there, so I think that's like easier to explain. But overall, the way we did it is like we just added noise to left to right training. So we tried two things. One was like doing entirely random, and we found that that was a little bit worse because our evaluation criteria was entirely left to right. And if your evaluation criteria, because during evaluation we are using left to right factorization, uh, probably you want to be closer to the left to right factorization than doing entirely random. So our algorithm is something like this. I mean, this is far away from what is optimal, but it's better than doing entirely random, which is like you progressively keep adding noise to the left to right factorization, and you end up generating slowly like you keep going far away from like left to right to like entirely random, and you get something in between, and you can probably get a little bit better results than doing entirely random. Does that answer your question?
Yeah. Okay. But so during training, is the model given some context on how does the model know that its training data is randomized or ordered?
No, it doesn't. So, that is one good thing about this experiment. So we actually tried two experiments. One was, there's this thing. There are papers like RAR and Sigma GPT. I don't know if you're aware of them, but what they do is like they have this thing called as target positional embeddings, and they tell the model using the target positional embedding what it's supposed to be predicting, and you could do that. But in this, but then that conflates a bit, because then you're adding all these other things and you're making things complicated. I like this experiment more because it's very simple, and you don't add anything. You just randomly factorize. You just randomize the order, and you keep everything else in the model architecture the same. So the model can itself figure out what order it is, because the number of n is very low. So if you have like n tending to like the highest possible value, I agree, it's like a extreme, it'll over regularize the model and it's extremely difficult to solve. But if you have n below 16 or something, then the model, by looking at first few orders, it can first few tokens, it can do a classification algorithm in its weights to figure out, okay, out of these 16, maybe it's the 14th one. Okay, then let me use that to predict the next token. uh, so yeah.
Got it. Yeah, makes sense.
Hi, Mihir. Thank you for your interesting work. I'm also very interested in the permutation experiments. Um, but I didn't find it in your GitHub repo. Do you have any plan to release that part as well?
Yeah, so we have like this second last. So we are thinking of releasing like we're thinking of releasing all the we plan to release it. It's just like we want to release all the section experiments, and each of them have like different strategies. Like each section in the paper, each experiment section in the paper has a different strategy. So we just want to release each one by one. So that's why it's taking time. But we'll release it in a few days, or 1 or 2 weeks or something.
Oh,
Um,
nice. Yeah, that'll
yeah,
be great.
yeah,
Yeah.
like yeah. Yeah. Overall, it should not be too difficult. Like mainly, we follow this pseudocode, and the main thing to do is like you have to somehow. It's a little bit complicated to implement because you have to somehow do it in rope, uh, because you have to handle this relative positional embedding. So there's little bit of complication in that implementation. But other than that, if you do absolute positional embeddings, then this is very straightforward to implement. Um, yeah.
Okay, so when you permute, you also tell the model this token actually from a different
Yeah,
place.
yeah. You need to maintain the positional embeddings to tell it
Got it. And the other setting is similar, the same as your mean experiments, or it has a different setting, or
no,
um,
it's the same. So
okay.
that like the experiment is in like 100 million token regime with 100 epochs.
Okay, okay, that's good to know. Thanks.
Thanks.
I have a question. Currently in time series data forecasting, people are trying to like combine autoregression and diffusion models. And what do you see like for those hybrid models, like combine both diffusion and autoregression? What do you see? Yeah, what
I think a good question here is like, what part of autoregressive do you want and what part of diffusion do you want? Because there are like a lot of things in autoregressive and diffusion that are very unique. Like for instance, like if someone cares about like for instance, autoregressive does like causal attention and diffusion does like bidirectional attention, and because of which autoregressive has like higher throughput. Now, do you care about higher throughput? So along what axis do you want to interpolate between the two? That designs like how should you interpolate between the two objectives. So there are papers like block diffusion, for example, and for them they care a lot about compute efficiency during training. So for them, that's why they design this algorithm of block diffusion, which allows them to interpolate along this axis. For us, we care a lot about this compute data trade-off. So there's a different way to interpolate between these two objectives. And there are a lot of papers that propose like different axes of interpolation. I think it comes down to like, what do you care about? Like along what axis do you want to interpolate? But overall, this is a good direction, which is that how do you get benefits of both objectives, like the trade-offs of both objectives. Um,
Also, what do you see like because for diffusion, when you I mean the sampling I mean when you perform inferencing, it needs a lot of time steps to perform the sampling. Like
it actually doesn't need a lot of time steps. So it needs lesser time steps than autoregressive. So for example, in autoregressive, the number of time steps is equal to your sequence length because you're predicting one token at a time. In diffusion, it's actually lesser because you're predicting multiple tokens at a time. But so that's why in diffusion, usually latency is much lower than autoregressive because you're predicting multiple tokens at a time. But then what happens, the issue with diffusion is like you're not doing KV caching. So because of that, now you have like lower throughput than autoregressive. So like I think like these are all like trade-offs that you have to make. But overall like I just believe like we should not like overemphasize on the word diffusion or autoregressive. And I think like the right trade-off that you want is somewhere in between for both of them. Like it depends on what you care. Like if you care about latency or do you care about throughput, like stuff like that.
Okay, thank you.
Any further question? We have a question in the chat. I'll read it out. Do you think diffusion or data augmentation will remain effective as the data set size keep growing until reaching the total number of unique text data samples and reaching the end of pre-training, where the data space might eventually become more saturated?
I think this is a very good question. Like I think the answer for this is like you need to be smart about where do you want to do diffusion. So I would like to quote what the clone of Simo said in his tweet, which is that take your 1% high quality data and train for 100 epochs right now. So what he's trying to head towards is like you want data efficiency when you have high quality data, and you want compute efficiency maybe when you have low quality data or something like that. So it's not like you have to do like diffusion on the whole pre-training or something like that. Like there would be some interesting trade-offs that you have to study between these two based on data quality and all these things. I mean, I hope that answers the question. Okay.
Okay, it seems that we do not have further questions. Let's wrap it here. Thank you, Mihir, again for your amazing talk.
All right. See you guys.
Yes, you guys. Can you send the slides to my email or Xinyu's email?
Sure. Sounds good. Thanks.
Okay, thank you.